So here's what we've got. A population of insects, currently the number is 22,500, is increasing at a rate of R of t equal to 1,225 e to the 0.14 t insects per week. So starting with this many, increasing at this many insects per week. If the survival function is s of t equal to e to the negative 0.2 t, how many insects will there be in 12 weeks? So I would never know how to do this problem if someone didn't like show me the formula. So here is the formula, in case you don't remember it. P of t, the amount of stuff at time t, or the number of stuff at time t, or the population at time t, is S of t times P naught. Time plus the integral from 0 to capital T of S of capital T minus T times R of T dt. Okay, where capital T is the actual amount of time. So just to kind of run down what this is all about, right? Let me use a different color here. This first part here, this is how many insects that survive from the initial population. Right, the survival rate after we're going to plug in 12 for t here times the initial population, which will be 20,500. And then the way you should kind of think about here is this is the surviving members from t equals 0 to whatever the capital T is. Right, it's the survival rate. And that's both of these combined, right? So this is the rate of growth times the survival rate. Okay, I don't think we need to get too into this, but just kind of wanted to point out what these things are. Yeah, so for example, if t was 1, r of 1 would be the number of new members. Yeah, right, because we're saying we've got that many insects growing per week. And then S of 1 minus T, sorry, I've got this. It's hard, it's easy to make mistakes when you got two T's here. R of T minus 1, or sorry, S of T minus 1 would be the percent of insects that survive T minus 1 weeks. Yeah, okay. Anyway, we're going to throw it all in the formula. So here's what we've got. We know that S of T, so yeah, so I have to be super careful because it's easy to make mistakes. So the survival function is this, and the rate is this, and P naught is this. So putting it all into the formula, which I guess I'll need the other side of the board for. So we're going to have, and I should say capital T is 12 weeks. So plugging this in, we're going to get S of 12 times P naught. So we're going to get S of 12 times P naught, and we'll substitute things in a minute here. Plus the integral from 0 to 12, right? It's the integral from 0 to capital T of S of 12 minus T times R of T. So it can be a little bit confusing if we're not super careful where you're actually plugging in the time, right? You're plugging in the time here, here, and here. And then we should actually write the functions in. So, right, S of t was e to the negative 0.2 t. So we're going to get e to the negative 0.2 times 12. And P naught was, what was it? It was 22,500. Whoops, not 225,000. plus the integral from 0 to 12. Okay, s of 12 minus t. Well, s of 12 was e to the negative 0.02 times 12. S of this is going to be e to the negative 0.2 times 12 minus t. And then r of t, right? R of t is this 1,225 times e to the 0.14 t. Whew, okay. So there's the whole thing. We're going to do a little bit of simplifying, but it's actually, I know it looks terrible. It's actually not that terrible. So this is going to be e to the negative 2.4 e to the negative 2.4 times 22,500 plus the integral from 0 to 12. Let's see. So if we, let's pull this 1225 out in front. Integral from 0 to 12. I've got e to the negative 2.4. And then minus 0.2 times minus t is plus 0.2 t. But instead of writing it as e to the negative 2.4 plus 0.2 t, let's write it as e to the negative 2.4 times e to the 0.2 t times e to the, that should be 0.14, I believe. I think I lost the 1. Yeah, I did. Sorry about that. It should be e to the 0.14 t. Okay, so simplifying a little further, if you use a calculator, this number here is approximately 2041, just so we don't have to write all this garbage out every time. So 2041 plus this constant can come out in front as well. So you've got 1225 times e to the negative 2.4 times the integral from 0 to 12 of this. Now we can just write as e to the 0.2t plus 0.14t is 0.34t. So yeah, it looks terrible, but it's not that bad once you get down to it. So let's see what we've got here. So integrating this, right? We now integrate e to the something times t. The integral of this is going to be e to the 0.34t divided by 0.34. Right? That's the not terrible for integration. So we're going to get that this is 2041 plus 1,225 times e to the negative 2.4. And then the integral of this is going to be e to the 0.34t divided by 0.34 from 0 to 12. Whew, that's a lot. And then we can plug it in, right? So to plug it in, I guess I'll go up here since I'm out of room. So if we plug it in, we get 2041 plus 1,225. I'm going to rewrite this as divided by e to the positive 2.4, just because it's easier to write it that way. And then here, if I plug in 12, I'm going to get, let's see, 0.34 times 12 is a number. Where's my calculator? Missing. 0.34 times 12 is 4.08. So we're going to get e to the 4.08 divided by 0.34 minus e to the 0, so 1 divided by 0.34. And the rest of this problem is just throwing it all into a calculator. If you do that, you're going to get approximately 2041 plus 1225 over e to the 2.4. Oh, that's interesting. Oh, no, I see. And then this number here is about 58.15 divided by 0.34. And then using a calculator further, this whole thing becomes about 19,005. So we end up with approximately, I know we're running out of room here, 2041 plus 19,005, so 21,046. So this tells us that after 12 weeks with this initial population, this rate of growth, and this survival rate, after 12 weeks, we will have slightly less insects, right? We'll have 21,046. Okay. Is this interesting? I don't particularly think so, but it is definitely something that is in the textbook. So it is something to be aware of, right? If you see a survival renewal problem, you should immediately think, okay, I should go look up this formula, because you shouldn't memorize it. But it's on, I forget, it's like on page 400, I think, or something. So be aware of that. Do what you will with it. I mean, there is also the drug thing, but I feel like we can certainly do more of that if you guys want to. If you request it, I will do more of it. But I'm going to move on to talking about area and volume. So the quiz I'm going to post for you guys for this weekend will definitely have some area and volume questions on it. Again, I remind you, the quiz is low stakes, right? As long as you do it, you get credit. Like, if you do it all wrong, that's still perfectly fine. So I feel like I had a thing that I wanted. Where'd you go? Oh yeah, I know what it was. Sure. So just want to make sure everyone's cool with average value. So here's a real straightforward example. So I want to find the average value of f of x equal to, sure, 3x squared on the interval from 1 to 3. So you don't have to draw a picture. I'm going to draw a picture at the end. All you have to do is say, okay, to find the average value, I'm going to find the area from 1 to 3. And then I'm going to divide by how long the interval is. So I'm going to divide by 2, or multiply by 1/2. So that's going to be 1/2 of the integral from 3x squared is x cubed from 1 to 3. So that's going to be 1/2 of, let's see, 3 cubed is 27 minus 1 cubed is 1. That's going to be 13. And so what we're saying there, in case you've forgotten or hadn't heard, right? If your function is 3x squared, so it looks something like this, from 1 to 3, and I know if I plug in 1, I get 1. Oh, sorry, if I plug in 1, I get 3. If I plug in 3, I get 27, right? 3 times 1 squared is 3, 3 times 1 squared is 1. And what we're saying here is that the average value of this is 13. So if you could take all of the area under the curve here and make it so that it was the same base, but the rectangle of all the same height, the height would be this number here. And the idea is essentially that this part here would fill in this missing part here. That's kind of how I think of it anyway. So that it would all be even. Or you could think of it, as I said before, right? You could think of this part, right? You could think of this as the ant farm. And when you shake it up, right, it all levels out to being just at this height here, right? That's average value. Same amount of area, just all at the same height is what average value is that height. But we can use this concept to actually answer some other questions. So I know I said I was going to do area and volume, and I'm doing some average stuff. That's okay. We'll get there. It's good to do a few word problems here and there to make sure we're thinking about what's going on. This class is, it's calculus with biological applications, so we should talk about the application sometimes. Let's look at this one. This is from section 6.2, number 13. In a certain city, the temperature in degrees Fahrenheit, T hours after 9 a.m. is modeled by the function the temperature, capital T, at time T, hours after 9 a.m. is equal to 50 plus 14 sine, what have I got here? Pi times T over 12, or I would probably write it as pi over 12 times T. You could also write that as pi T over 12, but I think this is a little bit easier to see. So find the average temperature between 9 a.m. and 9 p.m. Okay, so to do this, we're going to integrate, we're going to use the average value. So let me point out, if I did the integral, well, first of all, I'm not going to integrate from 9 to 9. That would be dumb. I would get 0. Second of all, I'm not going to integrate from 9 to 21, because even though that's 9 a.m. to 9 p.m., we know that it would be much easier well, in fact, I should have probably, right? Because this says the temperature T hours after 9 a.m. So at 9 a.m., time is 0. So we should be integrating from 0 to 12 of this function. 50 plus 14 sine of pi over 12 t dt. Now this here, if we calculated this, it would be kind of silly. This would give us the total temperature over those 12 hours. So this is going to be, I don't know what this is exactly. It's going to be something like, I don't know, 700. It doesn't really make sense to talk about the total temperature over 12 hours being 700 degrees, right? That seems like a ridiculous thing to say. Instead, right, we're going to be calculating the average temperature during those 12 hours. So we're going to do 1 divided by 12 minus 0 times interval. So that's how we calculate the average temperature in this city. It's not too awful. Always sounds so winning, right? I'm like, this integral is only mildly terrible, right? I mean, that's kind of how it is. They're usually all kind of awful. Some of them more so, some of them less. So if we integrate this, we get 50t. The integral of sine is negative cosine. So we're going to get negative 14 sine of pi over 12t. And then we're going to have to divide that by pi over 12. Sorry, I said cosine, I wrote sine. Apologies. Right, I just want to remind everybody, when we integrated sine of pi over 12t, we got cosine of pi, negative cosine of pi over 12t, and then we had to divide by the coefficient of t here, the pi over 12. Okay, so then we plug in our limits of integration. We get 1/12 times, let's see, 50 times 12 is 600, minus 14 times cosine of pi over 12 times 12. So let's see, pi over 12 times 12 is pi. Cosine of pi is negative 1. Negative 14 times negative 1 is plus 14 over pi over 12. Minus, then we plug in 0. 50 times 0 is 0. Minus 14 times cosine of 0 is 1. 14, right, cosine of 0 is 1. So we get 14 times 1 over pi over 12. So another 14 over pi over 12. So this ends up being 1 over 12 times 600 is 50. And then 1 over 12 times 14 plus another 14, so 28. And instead of dividing by pi over 12, let's multiply by 12 over pi. Probably could have done that sooner. But the 12s cancel. So our average temperature is 50 plus 28 divided by pi, which is approximately, I don't know, 28 divided by pi is probably about 9. So I'm guessing approximately 59 degrees. Let's see what that is actually. Yeah, 8.9. It's a good guess, James. Good job. About 58.9 degrees. Not a very warm city. Or not a very warm time of year. Okay. Enough. So again, average value, right? You're just taking the integral and dividing by the difference between the limits of integration. So where did my other examples go? Yeah. Okay. I feel like, yeah, have I said enough about area? What time is it? Yeah, I should probably, I think I'm going to move. So I'm going to move into volume. I know I said area, but I feel like we talked about area and we need to talk about volume. So they're very related anyway. So we'll talk about kind of both of them. So I want to find, let's talk about this one first. Yeah. So find the volume of the solid formed when the region, these always take so long to write out, formed when the region bounded by the following: y equal to x cubed, y equal to 0, and x equal to 2 is revolved around the x-axis. And most of the time with these types of questions where you're trying to find the volume of revolution, you're almost always going to want to draw a picture. Like you can do it without drawing the picture. It's easier if you draw the picture. So I need to draw y equals x cubed, y equals 0, and x equals 2. Two of those are pretty easy. Not the pen I was hoping for. So y equals 0 is the x-axis. X equals 2 is a vertical line at x equals 2. And y equals x cubed looks like this. So it's going to do something like this. Like that. And there's clearly a point of intersection here at 0, 0. And there's also a point of intersection here. Now this one's easy to find because we know that this point here, x equals 2. So if you've got y equals x cubed and x equals 2, well then y has to equal 2 cubed. And it's usually a good idea to find the points of intersection when you are trying to deal with this sort of thing. So I'm going to redraw this because I don't need all of that. I really just want kind of the part. So it's got to be bounded by this and this and this. So it's got to be this region here. Okay, so there we go. X equals 2, y equals 0, y equals x cubed. And we're revolving around the x-axis. And I'm going to make a blanket statement here that is true in this class. The axis you're revolving around completely determines whether you're using vertical rectangles or horizontal rectangles. Your rectangles have to be perpendicular to your axis of rotation. So, since we are rotating around the x-axis, which is a horizontal axis, our rectangles have to be vertical rectangles. And the reason is because the method we're using, which is called the disk method, right, relies on these rectangles rotating around the axis of rotation that they're perpendicular to and making a disk. So I'm going to erase this right here so I can kind of draw what's happening. So we're going to revolve this around the x-axis. I'm going to draw, and so this picture you need, this next picture you don't really need. You certainly are welcome to draw it, but you do not have to draw it. Now let's try to be precise here. Sure. Yeah, cool. Yeah. So here's the way I'm going to draw this picture. I'm going to draw the revolution, and the way I really actually draw it is I draw kind of the outer boundary that's away from the axis, and then I draw the reflection of that. So maybe like down here. and then I try and make it look 3D. That's not my best. I'm not gonna lie. Right, but that's kind of the idea. Specifically, I'm really interested in what's happening with this rectangle. So when that rectangle rotates around, right, it's going to look like a little disc. And I know how to find the volume of that disc. The volume of that disc is equal to pi times the radius squared times the thickness, dx. So I'm going to go back and be a little more specific, right? This disc has a radius that is just the height of that rectangle. Hopefully you guys can see this all right. I know it's a little smaller right here. So let me actually draw this disc out here. So this disc, so I'm going to kind of draw a little bit larger. Right? The radius of that disc is just how tall your rectangle is. That's just the function. So in this case, it's going to equal x cubed. And the thickness of your disc is just the width of your base of your rectangle, which is just dx, right? That's it, right? Again, going back to like the Riemann sums stuff, this is just a small change in x. It's your delta x, it's your dx. So the volume of this disc in red here is pi times, sorry, let me say this again, is pi times x cubed squared times dx. All right, and then the whole idea is that I don't want the volume of just that one disc. I want the volumes of all the discs added up together, which is going to be hard for me to draw. Right, so hopefully you get the idea, right? Right, if we're trying to add up all the discs, we're going to use an integral. So the total volume is going to equal, if I add these all up, so I'm going to integrate this pi times x cubed squared dx from 0 to 2. Right, we're adding up all the discs that occur from x equals 0 to x equals 2. The disc, right, the discs to the left have a smaller radius. Right, when x is like 1/2, the radius is really tiny. It's, it's 1/2 cubed, which is 1/8. Whereas when you get all the way out to 2, right, the last kind of disc, okay, that's terrible. The last disc has a really big radius, right? It's 2 cubed, which is 8. So we're adding up all the volumes of these discs. The calculation itself is not that terrible, right? This integral is fairly straightforward. So that's going to be, that's the integral. So usually put the pi out in front. You get pi times the integral from 0 to 2. X cubed squared is x to the 6th. And then you just do the antiderivative. So you're going to get, I'm going to erase this here. You're going to get pi times x to the 7th over 7 from 0 to 2. 2 to the 7th is 128. So you get 128 pi divided by 7. Okay. So, again, right, the radius is just the distance to the axis of rotation. So the radius, and it's typically just going to be what your function is, right? Because it's how far you are from here to the axis of rotation. So like, right, at 1, the radius is 1. At 2, the radius is 8. and so on. Okay. Let's do more. Let's actually continue with this example because now I want to ask the question, what if instead we revolve it around the y-axis? Take the same region. Let's see. Yeah, let's see here. Here's my same region. X equals 2. Y equals 0. I guess I could draw x equals 2 over here. And y equals x cubed. And now we're revolving around the y-axis. So here's how it's going to look. How do I want to do this? Yeah. Let's draw it over here. So again, you don't have to draw the 3D shape. If you want to draw it, the way I usually do it is I try to take the region and just draw its reflection in the axis. So I'm going to draw this, and then I'm going to draw the reflection over here. It doesn't have to be perfect. Clearly it's not. And then, so this one, right, you've got kind of like, what I think of as like, you've got like a cylinder, and then you've taken out like a big bowl kind of from it. So we've rotated this around. Yeah. My drawings always kind of get a little interesting here. I guess you'd be able to see that part. And sometimes, right, like if you're trying to make it look. I guess you wouldn't see that part really. Or you could do it more like this. Okay. So hopefully you get something from that, right? You kind of see like, oh yeah, you've got this cylinder, like this block, and then you've taken out a bowl. That's the way I'm seeing it. Yeah. So, right, there's like, that doesn't really help. That doesn't make it look any better. Okay, so again, I'm going to come back to reminding everybody that when you're rotating around an axis, you have to use a rectangle that is perpendicular to the axis of rotation. So we have to use a horizontal rectangle here. And now check this out. I should use a different color. Tracer, yeah. So here's the deal. This is kind of important. When I rotate this around the y-axis, there's some space, right? My thing isn't right next to the axis of rotation. Or as I like to say, it's not, my region isn't flush with the axis of rotation. So when that's the case, or when I rotate this little strip around the axis of rotation, sorry, it's try to make it look good. We get a washer, right? If you take this little horizontal rectangle and rotate it around this axis, you're going to get an outer circle, but you're going to be missing this inner circle. So the volume of our washer is what I like to call pi times the big radius squared minus pi times the little radius squared times the thickness, dy. Right? This thickness is dy. And come on, James. This length here is your large radius. And I'm running out of room. Sorry. I guess I'll do it up here. this length here is your small radius. So the big circle has an area of pi times big R squared, and you're subtracting out the little circle that has an area of pi times little r squared. And then you're multiplying it all by the thickness, which is dy. So if your region is flush, right, it lives against the axis of rotation, you don't have to worry about this. You're not going to be missing any kind of middle part. But if your region does not touch the axis of rotation the whole time, you're going to have to use this thing where you're subtracting out the middle part. So this is called the washer method. The other one is called the disk method. They're really the same method. It's just that the washer method, there's an additional thing you have to subtract out, whereas the disk method, there is not. Either case, to find the volume, so again, right, we're adding up. So no, I should not. Like, so yeah, we're adding up all the washers. I was gonna try and draw it, I can't draw it. There are good pictures in books about like showing the slices. In fact, I wonder now if your book has good pictures. Let me take a look real quick. Section 6. Yeah, your book's got some. Yeah, totally. Oh yeah, your book's got great pictures. Look at the pictures in your book. They do a good job of kind of getting at the point of talking about how you're adding up all these slices of discs, or adding up all these slices of washers. And then we have one more, it's actually a bunch of slices of washers. But okay, so to find this volume, we're going to add up all the washers, and the washers go as low as 0. And the washers go as high as 8. So when you're doing things with respect to y versus respect to x, often your limits of integration are going to change, right? For this one, the vertical slices went as far left as 0 and as far right as x equals 2. For this one, the horizontal slices, which are washers, go as low as 0 and as high as y equals 8. And then we're just doing, I guess I should have, we're not quite there yet. I should factor out the pi. But then I actually need to identify what the big radius and the little radius are. So, pun not intended there with the r and the radius, but it's a good one. So the big radius is the distance from the thing that's further away from the axis to the axis. In this case, the big radius is just 2. The small radius is this distance here. So the small radius is going to change, right? When you go lower, it's very man. Okay, sorry, that's terrible. No, that's right. Yeah, when you go lower, the small radius is really short. When you go higher, the small radius is really big. So when you have a really high up one like this, you have like a really kind of long, silly looking washer. Oh, come on, James. You can draw this, right? Where it's like it's almost like a rubber band, how big it is. And I've not drawn that very well. But my inner radius here is, it's this distance here. So it's just this function, which is not, it is y equals x cubed, but we have to solve for x as a function of y. So this inner radius, the smaller radius, is going to be not y equals x cubed, but x equal to the cube root of y. And we know it has to be in terms of y because of the dy, right? The d whatever tells us that's the variable we have to be using. And we knew it was y because we knew we were using horizontal strips or horizontal rectangles, whatever you want to call them. What time is it? Evaluating this is not super challenging, right? This becomes pi integral from 0 to 8 of 4 minus the cube root of y squared is y to the 2/3. So integrating, we get pi times integral of 4 is 4y. Integral of y to the 2/3 is y to the 5/3 times 3/5 from 0 to 8. And then we plug in the 8 and we get pi times, 4 times 8 is 32 minus y to the 8 to the 5/3 is 2 to the 5th, which is also 32. So it's 3/5 of 32. And plug in 0, you get 0. So this is a number. You could factor out the 32 here and say it's 32 times 1 minus 3/5, which is 2/5. So it's 32 times 2/5, which is 64/5. I'm not focused so much on actually finding the value. Like getting to this stage right here, that's the most important part of this process. Yes, it's also important afterwards to be able to do the antiderivative and to calculate things, but setting it up is kind of the hardest part, and the rest of it is usually not quite so awful. Okay. Yeah, cool. All right, yeah, let's look at another one here. We should have enough time to get through this one. This one we will just focus on the setting up and not the evaluating. I will also mention most of these volume integrals, or I should say most of these volumes of revolution integrals, usually the integration isn't too terrible. Usually it's just powers of x or y and not anything else. Not always, sometimes there's other functions, but most of the time they're not like do a crazy u sub in addition to this stuff. It's usually just like, it's a pretty straightforward integral if you're doing volume. Most of the time. Okay, so let's look at this one. Set up the integral for the volume of the solid formed when the region bounded by, so the region is bounded by y equal to x squared, y equal to x plus 2, and x equal to 0. It is revolved around each axis. We'll do the x-axis first. I should say in quadrant 1. All right, so let's take a look. We're going to graph these, but I'm also going to point out it's good to find where they intersect each other. So like you can find where these two intersect by setting x squared equal to x plus 2. Sometimes you can just guess, right? Like I can guess pretty easily that x is 2. 2 squared is 4, 2 plus 2 is 4. You could also like factor x minus 2 times x plus 1. So you get x equal to 2 and x equal to -1. But we don't care about this one because it's not in the first quadrant. So here's what we've got. We've got x equal to 0. We've got y equal to x plus 2, which looks like this. And we've got y equal to x squared, which looks like this. So that's our region. And we're rotating around the x-axis. So again, I'm going around the horizontal axis. I'm using vertical rectangles. And hopefully everyone can see at this point that our rectangle, our arbitrary rectangle that we drew in the middle, right? You don't want to draw the rectangle at the end, but the rectangle we drew in the middle isn't touching the axis of rotation. Okay, that means we're going to have to use the washer method, right? We've got, right, this is our little strip that we're revolving to get a washer. So the volume of this washer is, again, we can factor out the pi. It's going to be pi times the big radius squared minus the little radius squared times dx. This is always where I'm starting, either the volume of the washer or the volume of the disk. It's either pi r squared d whatever, or pi times big R squared minus little r squared d whatever, depending on if it's x or y. Okay, the big radius is the function that's further away from the axis, so that's going to be x plus 2. So this is pi times x plus 2 squared minus the inner radius, which is x squared. I think this is a good question because if you don't draw it out, a lot of people make the assumption incorrectly that x squared is the bigger function. But if you draw it out, it's very, very clear that x squared is not the bigger function in this region. So then the total volume is going to be the integral. I'm going to put the pi on the outside of x plus 2 squared minus x squared squared. Yes. My lower left limit of integration, right? The left, so this goes as far left as x equals 0. This goes as far right as x equal to 4. X equal to 2. Sorry. And that would be how we set this one up. Let's go around the y-axis. Okay, so same region. Sure, same region. But now we're going around the y-axis. So we need to use horizontal strips or horizontal rectangles. And there's an issue here. And the issue is that we have different boundaries depending on how high up we are. So down here, if this is our rectangle, then we're going to be using the disk method, right? Because when we rotate that around, it's just going to look like a disk. But I can draw up here, I think. Yeah, cool. When we're up here in this region, the rectangle isn't touching the axis of rotation. So when I rotate this little rectangle around the axis of rotation, I'm going to get a washer. We're going to have to do two integrals, right? Because the horizontal rectangles have different boundaries depending on where we are. So from y equals 0 to y equals 2, right? That's the point 0, 2 right there. We're going to use the disk method. So for the disk method part, the volume is going to be pi times the integral from 0 to 2 of my radius squared. The radius here, well, this function is the function, sorry, I've lost space here. That's y equals x squared, so it's x equal to the positive square root of y, since we're on the right side. If it was on the left, it would be the negative square root of y. I know we're out of time, so let me just finish this. And then for this upper part, we'd use the washer method. So it would be pi integral from y equals 2 to y equals 4 of my outer radius squared minus my inner radius squared. My outer radius is actually the same as it was down here, right? The right hand further away from the axis function is the same anywhere we are in this region. So the outer radius is going to be the square root of y. The inner radius is this straight line, which was y equals x plus 2. But again, we have to solve for x. X equals y minus 2. So that would be the setup for the volume rotated around the y-axis. So words I'll leave you with for this kind of stuff. When you're finding volumes of revolution, make sure that the rectangular strip you are thinking of is always drawn perpendicular to your axis of rotation. It does not work if you draw it parallel.